have one equilibrium point, and that is the origin, and your nonlinear element is an odd quadratic, which is to say it's going to do something like that. And that's not going to move your equilibrium point. There is no constant perturbing you from 0.
How would you get a constant?
In block diagrams, that's the constant that it would be something like that. And put it in wherever you feel it might come in, you know, as part of the plant, and that's going to move you, but that's how you represent it in block diagram. What effect it would have, I would have to think about, but if it isn't there, it's relatively straightforward. Shoot.
Can you just run through your thinking on, or your logic on B again?
Which part is B?
Just so, what will YT be doing at T equals infinity?
So the first part of that is the limit cycle stable or unstable?
Okay.
If the limit cycle is stable, and there's only one of it, we're going to the limit cycle.
Okay.
At least mathematically, we've made some assumptions. Real system might not do this, but
Yeah.
to the level of this analysis, we're going to the limit cycle.
Yeah.
If the limit cycle is unstable, we're going away from the limit cycle.
Okay.
And if we start inside it, that means we're going down to 0. If we start outside it, we're going off to infinity.
Okay.
We don't this analysis doesn't tell us oscillating, doesn't tell us, exponential decay versus oscillatory decay, but we know where we're going as t goes to infinity.
What if it had turned out to be stable? Would you have to calculate the limit cycle?
Only if it asks for it. It would probably, for a describing function question, be sufficient to say it will oscillate with such and such frequency and such amplitude. Because to the level of describing functions, that is what it does.
So there's nothing like final value theorem equivalent?
You're not happy with it having the frequency and amplitude of your oscillation? That's not good enough?
It's easier to just like plug in 0. I mean, because when I looked at the problem, my thought never went to stable limit cycle or whatsoever.
The setup of the problem should help you solve the problem. If you look at it and go, this is a Nichols problem. Nichols produces these answers, right?
I suppose.
This is how to game the system in terms of all exams, not just this class.
I suppose.
Can I erase? Cool. We'll probably take like a 5-minute break after question 3, just to not go on forever, unless I get unanimous agreement that no one wants a break. What does question 3 ask?
Consider the system x double dot plus x dot plus x. Shown all this.
Oh yeah, this one. Okay, cool. I'm caught up.
Okay, so consider the system x double dot plus x dot plus x minus x cubed equals 0.
Uh-huh.
Let b equals half x dot squared plus half x squared minus a quarter x to the 4. A plot of the contours of b is provided. In what region of the state space is b positive definite?
It's something like this.
Yep.
All right. So this is our V contours, and then B itself is dot squared plus x squared minus 1/4 x to the 4th, something like that.
Yeah.
Cool. Where is this positive?
Everywhere.
Are you sure?
No, I think
No. Oh, I think it's the
Everywhere
minus.
first.
Yeah.
Yes. So, given the contour plot, all we really need to do is pick out what the 0 contour is, right? And first easy thing to check is, what if x was 0? Then it's positive everywhere, right? So we know that it's positive on that axis. Next thing to look for, what if x dot was 0? Then we'd have right? Which means either x equals 0 or 1 minus 1/2 x squared equals 0. Which means x is plus minus square root 2. And if I recall, there was a 1 there and like a 1.5 at the edge, something like that. So that means that somewhere over here, we're going to have a pair of contours at the square root 2 plus and minus square root 2 that are the 0 contours. And I'm just going to copy that down here in order to shade in the positive region, right? Okay, everybody see how I took the contour plot we were given and a little bit of poking at V to get to which contour is the 0 contour?
So I guess it would have been a little clearer if it was like a positive greater than 0.
Oh, this?
Yeah, but,
I'm solving for the 0 contour,
yeah,
because that's going to divide positive from negative.
right, but yeah.
So it's basically the whole image?
Except everything you're shown in the plot pretty much, but there will be vast regions of space off to the sides where it isn't.
So you just plus minus 2?
Square root 2.
Square root 2.
Yes.
Because if you find the gradient, you can check see whether Hessian is positive, something like that. So maybe not. Like to tell whether a matrix is positive definite. or medium
Right,
line.
but this function is not determined by a matrix. This function is,
Sorry, like for you, to check whether function is positive definite, can't you check the Hessian? We can, never mind. I'll take your word for it. Cause I was gonna have like a matrix representation and find the eigenvalues for it and like how I
I think all we care about, does it ask for positive definite or does it ask for where B is positive?
positive definite,
Strictly positive though, right?
yeah.
So where is V strictly positive? That's everywhere between those two contours. Right?
Is that like the best method to finding regions like this? Because I guess it never occurred to me to go this route initially, and I just read this now.
For any kind of problem like this, it's just kind of poke and prod at it. If you're given some of the contours, poke and prod and do a little bit of investigation to see if you can nail down one point. The check for, when x is 0 on the center axis, is that positive or negative? That part matters too. Like it isn't just the second half. Because if the center was negative, the 0 contour would tell us that it was positive out on the sides. Yeah. All right. We've got our region where V is positive. What's next?
And what region of the state space is V dot less than or equal to 0?
Right. V dot, x dot plus, x dot, x double dot plus x dot minus x dot x cubed, something like that, right? And when I plug in on x double dot, I'm gonna get x dot minus x dot x minus x dot x cubed minus x dot squared plus x dot plus, that was plus, this one's minus x dot x cubed. This term cancels this term, and this term cancels this term. Right? Minus x dot squared. Negative semi-definite everywhere. Right? What's next?
I have a question.
Shoot.
So when it's a negative semi-definite, it means that your energy is decreasing. You can see it like that, but what does it mean for V to not be positive definite?
So you mean O. So in general, our arguments around, if we've got state and V, we're trying to formulate some kind of a bowl and then say we're going downhill. V being not positive definite means our V comes down like this. And so saying we go downhill does not mean we're going towards the origin anymore. Does that make sense?
Okay. And couldn't you still like loop around or something like that?
You could, but we can't use this V to prove that you will. The argument, I'm going downhill, therefore I'm going towards my low point, only works when your low point is the bottom of your bowl. And if you've got a case where downhill could be down to minus infinity, you can't assert that you're going to the bottom of your bowl.
Could you have a negative definite V and a positive definite V dot? Just
Multiply through by a negative sign, and then everything applies exactly like you want it to, yes.
okay, got it.
Yep. All right. Last part, I think.
Part C, in what region of the state space can you claim stability?
Yes. Where can we claim stability?
Inner, the eighth region,
Where?
where you shaded A.
No.
No? Okay.
We do not need, we need one more thing.
Radio.
Yes, or as I prefer to call it, closed contour.
So it's a ball or circle with radius square root.
It's go to the plot that you're given, and the x bounds are 1, the y bounds are something tighter because v is not just a circle on x and x dot. So it's a little bit smushed.
But it's not a circle.
It's an ellipse-like shape.
So why the closed contour as opposed to something that can go off to infinity?
Yeah, if you don't have a closed contour of v, then we aren't able to argue that decreasing v will take us to the origin. We're trying to say that once you're inside this contour, v is a little bit lower than the value at the contour, and so if it goes downhill, it can't ever, if it decreases, it can't ever leave. If the contour isn't closed, it might be decreasing, but there is no contour to bound it to say it can't leave. It could, in fact, from outside this contour, without ever crossing a contour go off to infinity.
So are you saying that it is the smallest contour visible in the plot, or are you saying that?
The largest closed contour.
I don't think it's one of the ones that's shown in the plot.
Correct.
That's what I'm
You can
clarifying.
infer very slightly that there is a contour that crosses at one that is closed.
But it will like have the ratio that of like the but
Yeah, so this contour at one wasn't drawn, there was instead a contour that came very close to hitting the axis on each side,
Sure.
right? And from that you can go, okay, there's one that's gonna be closed right there at one.
but square root 2 is like 1.4, isn't it?
Right, that's the zero contour, this is the closed contour.
So it is like not with the radius axis, primary axis radius square root 2.
So-
It's like whatever biggest that we can fit.
The cross section here, if we've got V going up, is a bowl and a bump on either side. And so our V greater than zero region is here, but our closed contour is, I think it's peak to peak. I think our largest closed contour goes basically from the peak to the peak.
Okay.
And what this is gonna give us, if we did a 3D plot of this V, the contour at one is gonna be the ring that is this peak going all the way around. And the V value at the top of that peak is gonna be kind of the bound on once V gets below that, inside that contour, you can't ever increase V, so you can't get back to that contour, so you can't escape. Final part?
Just before we go, just
Sure.
last thing, so if you want X, you can find, if you find X from that, do you need to also give X dollars percent? Yeah.
You don't have to solve for it. If you say it's an ellipse-like or ovoid contour that passes through 1 and -1,
That's not.
or you draw on the plot, I think it's about here.
Okay. Yeah, because at that point, it's like your V is almost 0, but it's not quite, right?
Yes.
Okay.
So if on the exam you had basically torn off that page and stuck it in and, heavily drawn over that and heavily drawn over this and then shaded this, you can use that to mark, here's the regions.
Okay.
You've typically only got one copy of the exam, so be careful with how you mark those up. Do it in pencil if you're not 100% confident.
You have to do it in the blue book.
If you stuff your exam page in and write in the blue book, hey, look at my exam sheet for this part. We would obviously prefer it's a little simpler logistics if you're able to copy it across nicely enough. And seriously, that sketch is the level we're looking for in terms of, we're not looking for amazing drawings. That ovoid copied out, so, part C would be that would be full marks. We're not looking for anything fancy.
Wait, why is this only 1 meter 1?
It's the closed contour that goes through 1 and -1.
Near, okay.
Near,
Yeah,
through,
yeah.
right?
So is it stable? Is the question.
Yes. In that region, we can prove stability.
The
Using
question
this.
is it asymptotically stable?
Ah,
No, but C, I
That's
think
a
you were
different
asking C.
No, I was asking you.
Oh,
asymptotically stable is another step.
correct.
Is this the difference Rock keeps mentioning about whether it's like e to the negative lambda versus like some other function, or are we just saying?
Exponential.
That's
That's
exponentially
Right.
stable.
But stable and
asymptotic.
asymptotically stable.
Goes to equilibrium.
So against time, there is an exponential decay curve, e to the minus t, e to the minus alpha t, right? A system that decays faster than some exponential time constant. Don't care what shape it takes, it might reach the axis in finite time, anything like that, that is faster than e to the minus alpha t is exponentially stable. if it's getting to the axis, but it's doing so slower than any exponential you could set, then it is asymptotically stable, but not exponentially stable.
Okay.
Does that clarify?
I guess I don't know why, whatever, never mind.
It matters a little bit if you care how quickly your system gets there.
Right, but if I just said stable, that doesn't really say which you're looking for. So if we just say
'Cause
asymptotically stable.
Stable doesn't even imply that. Stable in the sense of Lyapunov just means it doesn't blow up,
Okay, cool.
right? So far, we've only proven stable in the sense of Lyapunov.
Okay, but asymptotically stable.
Asymptotically stable, we now need to go to, we will get to the subset of that where V is equal to, where V dot is equal to 0, right? With invariant set theorem. And V dot is equal to 0 when X dot is equal to 0. So on the axis is where we could come to rest by invariant set theorem. So we need to check that for equilibrium points.
Whether Vx equals 0?
Where V equals 0, sorry, where V
Sorry,
dot
yeah,
equals
V.
0 is going to be our invariant set,
Correct,
or our candidate invariant set.
correct.
So now we're going to look for equilibrium points on X dot equal to 0. And equilibrium points on X dot equal to 0 are X double dot plus X dot plus X minus X cubed, something like that. That's our dynamics.
Yep.
Equal to 0, equilibrium, equilibrium, so X, 1 minus X squared, equal to 0. X is equal to 0, plus or minus 1, right? So we've got equilibrium points right at the edges and in the center. And now all we have to do, there's a couple routes you can go to prove that it won't go to the plus or minus 1 points. You can evaluate V at those points and find that it is higher than the bottom of the bowl. Or you could do first method of Lyapunov. Yeah, those are the two.
Linearization?
Yeah, so you can linearize it about this point, and I think you're going to find that it's got one positive, one negative eigenvalue. I did not go about doing this. I just plugged in the V value, V of X equals 0, X dot equals 0, sorry, X equals plus or minus 1, X dot equals 0 is 0, 1/2 minus a quarter, right? Which is greater than the value at the bottom of the bowl. And
What's up? Yeah, proving it's not on the bowl.
That's the,
so what that says is any point off of that equilibrium point, there will be a very narrow set of trajectories that are exactly balanced to come to those marginally stable points, but they're not a low point you're going to settle to. Like our contour plot of V doesn't have a circle around here where it could be the bottom of its own little bowl. It's,
It has to hit that point exactly.
yeah,
Okay.
it's marginally stable.
Okay.
What we're checking with V at X equal 1, oh, I suppose I should also evaluate V of 0, 0 is 0. So V of the origin is lower, V of those other equilibrium points is higher. So we're going to go to the origin. All right,
So it's asymptotically stable.
yes. 5-minute break and come back for problem 4 and 5. I will see if I can rustle up some better pens.
Kill mine. So if we found that both of, if the v at 0, 0 is non-negative,
It had better not be negative. We want V to be positive definite. Right?
did I say negative? Sorry, it's positive. Like I'm trying to say that both v values at all equilibrium points are non-zero.
Then you can subtract off the minimum value.
Okay, so whatever lower, we'll get to whatever is lower.
Yeah. If you got a case where your V has multiple values, then you could hit the bottom of each of them, but you should expect to have some kind of V dot equals 0 points in between that you have to deal with.
But I guess I'm trying to see whether I can detect, like, say, like limit cycle. Like, will it stop at limit cycle, or will it keep going, or will it get stopped?
So if you've got a limit cycle, you're going to have something like the bottom of this valley here is a ring that goes around, and that's your limit cycle. And then you might descend to your limit cycle or to the origin, depending on where you start.
So you can't tell.
Or, as it was in your homework,
Oh, this is like homework. Okay.
you might descend to your limit cycle, but the origin is this bump in the middle, and so that's your limit cycle, and there is no spot in the middle to descend to. For any system, I would have to design pretty hard mathematically a system to do this.
Wait, did you say that for the second case?
So the one on your homework, there was no bump over
Origin,
zero.
yeah, origin was stable.
It was like-
Origin was unstable.
Yep.
And we didn't. There were 2 critical points, and we didn't know whether it will limit cycle or like stop there.
Right. That one was interesting, and probably more interesting than you'd be given on an exam.
Okay.
Not guaranteed.
Okay. So that was a more special case.
That was to make you think about it.
You know how, I forget when you do it, but you like get an equation for when like v dot or m is 0, and then you do m dot evaluation, and get a set to prove out your asymptotically stable region.
Mhm.
Right? Can you apply that here? Or-
Yeah, that's in fact what we're doing when we find the region where V dot is 0.
Okay.
We're not bothering to say d by dt of this set, I'm going straight to what are the equilibrium points within it.
Okay.
So I'm not quite doing invariant set theorem the way we do. I'm probably not quite being proper, but it's going to work out the same.
Okay.
Where your V dot equals 0 region is your candidate invariant set, and then you look for where within that d by dt of that set is 0. But when it's just an axis, all I really need to look for is equilibrium points, right? Because it's not, the x dot equals 0 axis is not going to form any kind of a set that it can move between, because that's 0 velocity. I'm going to go search for new pens. Jenna, you may have both of these.
How could you do this to me?
I'll be back.
At least my whiteboard's like actually white, not
This is
transparent.
actually
Like
pretty
it's so
good.
much harder to see, I think. Your bars are higher. Like see how obvious those.
Getting the setting sun reflection off of it, that's so. Freaking Warriors, man. Rooting for the Canadians now. It's also my brother-in-law is from like a English course. So I felt it was a big rub it in. That's honestly why I wanted to come back to California.
See your question where you write down, just read on board, you write down.
when he was not writing in a straight line.
I love how the colors like,
Like-
okay.
Apparently I did it completely wrong.
I love how the colors
Least you
shouldn't
did it
even
though.
matter.
I should
That will be printed grayscale.
I have more important things to do.
I hope we keep the colors, man, it keeps with the month.
Oh my goodness.
Oh, that's what I was like, oh, it's a pretty graph. That makes the problem so much better.
But we're not gonna see the
This
colors.
is a pretty ugly,
So our exam's gonna be like
handwritten.
probably harder than this, cause Rock was like so pissed that the average was so high in the midterm, like he's gonna like get his ego up, it's being recorded.
Yeah, everything you've said is kind of cool.
I keep forgetting.
He seemed excited.
I don't think he was angry.
You think you
I
can?
think he was surprised he had an average above like 78.
Yeah. Oh, do you wanna see my machining results? Did I tell you I broke a tool?
Again.
Yeah.
Oh dear. After I told you to.
I ran into the table. What? I don't know how.
What tool did you break?
A 1/4 inch up cutting tool bit.
Okay, as long
But
as it
anyway,
wasn't anything important.
I mean, it's cheap-ish.
Yeah.
But yeah, so
That's okay.
I gotta sand them and finish them, but
More sanding.
it's sand better than steel.
I can't believe you went through.
Yeah, so this is what happened. I'm almost done. And the shampoo just got through my.
Like when you mess up an exam. Just know.
We're just like, I'm almost done.
So
And then
beautiful.
so I had to recut it.
It looks like some like, what is that, like protesting street art? Like those like avant-garde, I don't know, I'm thinking like those people who have like the really like simple designs to like protest. Just like, no flowers here.
Okay.
Is it like a sample actually, or?
That is supposed to be an apple.
It's an apple?
Cut
Oh,
this
like
way.
the core, I was thinking like a
Sand dollar.
Yeah.
That is what my roommates and my dad told me. But you see, as a
Just roll with
collection,
it,
they
man.
are fruits. So you're supposed to. That is also a fruit.
So that's the key.
Yeah.
Not quite everyone back. Missing one, missing bad.
That would be difficult, actually, never mind.
Hey, Dave, could you walk through that whole,
I was gonna do
your negative, your 0 on the axis, all that stuff?
How I found where V dot was positive, part A? Or, oh, you mean V dot negative?
Oh.
Got it.
Yeah.
Let's see.
CNC wood as well.
So V dot is negative x dot squared,
Right, that's expensive.
which is 0 only when x dot is 0. That gives us a candidate invariant set region of that.
Yeah.
We've also already found that we've got a closed contour passing through